Okay. In the last lecture, we discussed constraints, and in this lecture, we will continue and study the first order optimality conditions. These are called KKT conditions. So the KKT conditions are basically first order necessary conditions that a solution of a constraint optimization problem or nonlinear programming problem, as it is sometimes called, must satisfy. Now consider this problem, this objective function, and these are the equality constraints and inequality constraints. Now, since it is necessary conditions, so first we assume that X star is a solution. First, a regular feasible point. What is regular? That we have discussed in the last lecture. What is X star is a regular feasible point and also a solution of this problem. Okay, it's a local minimum point. So there are three things here: feasibility, regularity, and minimality. So the feasibility implies these two. Among the inequality constraints, there may be one set, which is the active set, in which case the function is equal to 0 at this point, and then there is another set, inactive set, in which case the constraint function is negative at this point. Okay. Now, regularity implies that columns of this matrix for equality constraints and columns of this matrix corresponding to active inequality constraints are linearly independent and therefore provide a complete basis for the normal space, which is orthogonal to the tangent subspace. Minimality implies that at X star, at the current point, there is no feasible descent direction. That is, no descent direction that is feasible, neither in the tangent space nor in the feasible cone. Now, this one, what are all the things implied by this? Let us analyze that a little further and see where we get. So first, no descent direction in the tangent space. And in that case, the negative gradient will be contained completely in the normal space. And therefore, it must be possible to express it as a linear combination of columns in this and this. That is, negative gradient is a linear combination of these columns and these columns with corresponding coefficients as lambda 1, lambda 2, etc. and mu1, a, mu2, a, etc. A is for active. You can write it in this matrix vector form or this open form, okay, with summations. Here, M is the number of equality constraints, always active, and P is the number of inequality constraints active at this point. So from here, if you bring it on this side, then you get this. This is one condition which a minimum point must satisfy. Okay. Now, this condition sometimes we will refer to as the gradient condition because this relates the gradient of the objective function and the gradients of the active constraint functions. Okay. Now, this is implied by saying no descent direction in the tangent space. Now, what do we get by checking no descent direction in the feasible cone towards the interior? If any mu k a that you get from here, because you get, I am telling, because you are putting this here, putting this here, putting this here, and from there you are trying to solve for lambda and mu a, right? That is what you would do when you try to express this as a linear combination of these things. So if one of the mu's you get is negative, then it will be always possible to find a descent direction which will make the corresponding constraint GKA inactive and go into the interior. And along that direction, you will get this as negative, which will allow descent. And for that, how you will work out the direction? You will say that the direction and the grad GK, that corresponding GK, their inner product is negative. That is how this will leave the boundary and go to the interior, because at the boundary GK x star is 0. As you go in a direction such that this is negative, you are basically going in a direction which is inclined towards the negative gradient of this. That means you will go into the interior. From 0, it will reduce, it will decrease on the negative side. And all other components along these vectors are 0. That way you can get a direction D along which the function would decrease. Okay? Because its component along that turned out to be negative. So the way to actually find that direction is first to take the negative gradient of this GK and then take its orthogonal projection along grad HI and grad GJA for all the J's other than K. That means you take negative gradient of this constraint function and then project it to the tangent space of all the constraints except this one. Okay. So you will get the requisite number of equations from here to determine all the other components of the direction. Okay. And since we get that kind of a situation where there is a decent feasible direction for a negative value of this, so from that we come to the conclusion that these all must be positive or 0. And that is the other minimality condition. So these are the two minimality conditions which we get by analyzing the condition that there should be no feasible descent direction. These scalar coefficients, lambdas and mu's, that we encounter here, these are called Lagrange multipliers. Now, whatever we have done till now, we streamline that and consolidate to get to the conditions. How do we streamline? We say that we do not like writing A here all the time. And if we consider a different point, then which ones are active, which ones are inactive, we don't want to get into that headache. So we say the way we got the active constraints in the reckoning, like that we get the inactive constraints also, with the extra condition imposed that for inactive constraint, mu j has to be 0. So this inclusion of inactive constraints will actually not make any real change in the equations. They will not change any implication. And in order to ensure that mu j is 0 for inactive constraints only, mu j is necessarily 0 for inactive constraints only, we include this. And this is called complementarity condition. That is, the Lagrange multipliers and the inequality constraint functions are complementary. If one is non-zero, then the other has to be 0. If mu j is non-zero, then this must be 0 and the constraint must be active. On the other hand, if the constraint is not active, then this is negative and this is not 0. So in that case, mu j has to be 0. That is the condition which we are imposing right now. So we include that and then put all the conditions together and say that if x star is a regular point of the constraints and a solution of the nonlinear optimization problem, then there exist Lagrange multiplier vectors lambda and mu such that all these conditions hold. From optimality, we get these conditions. This is a gradient condition, and this is a non-negativity conditions of the Lagrange multipliers for inequality constraints. These are the original feasibility conditions, and this is a complementarity condition. Okay, that ensures that for inactive constraints, mu j's are 0, and if some mu j is non-zero, essentially positive, then the corresponding constraint must be active. Okay? Now, these conditions together are necessary. Every minimum point must satisfy them, but they are not sufficient. That there may be some points which satisfy these, but are not minimum points. Now, what will be the use of these KKT conditions? Utility. The primary utility of KKT conditions is to test a candidate solution. If any of the conditions is violated, then the point is clearly not a minimum point because KKT conditions are necessary. However, if all the conditions are satisfied, then also we don't know for sure that it is a minimum point. For the time being, we call it a KKT point. And then we say that a KKT point has to pass through some further confirmatory tests to be accepted as a minimum point. So in a way, it can be a shortlisting condition, shortlisting criteria. Okay. However, in the case of unconstrained optimization, we saw that first order conditions are satisfied by a maximum point also, a saddle point also. Okay. Compared to that, here KKT conditions in the general case are a little more. Okay, not just the condition for a stationary point, because the gradient condition will be satisfied by any stationary point, even a maximum point, but this condition is linked directly with minimality. No other stationary point is obliged to satisfy this systematically. Okay, so this is linked to minimality, but that is not good enough to ensure that it is a minimum point clearly. Still, it is a little more than the condition of stationary point. Now, for many problems, sometimes not only checking, sometimes even identifying a minimum point is possible by just identifying a KKT point. For that matter, the question also arises, how do you identify a KKT point? KKT conditions are for checking, but nicely used for simpler problems, you can even identify a KKT point using these. So, why I say this? Because complete identification of a solution involves determination of these many unknowns. The variable vector x has n unknowns, and in case of m equality constraints, there will be m lambdas, and n and l inequality constraints, there will be l mu's. So this n plus m plus l. If you identify these many unknowns, you are done. You have got a point completely. If you have got a point completely. So KKT conditions give you these many equations. Okay? Because the gradient condition gives you n equations. This feasibility condition gives you m equations. And for G, they don't give you equations, but corresponding complementary conditions give you that many equations. Mu j dj equal to 0. So n plus m plus l equations you get. Of course, they are nonlinear in general. Okay, the complementary conditions are always nonlinear, bilinear to be precise. In fact, it depends upon G but whatever simple G is, it will be at least bilinear. So nonlinear certainly. Others also in general will be nonlinear. Now, to qualify as a KKT point, a solution of these n plus m plus l equations also has to satisfy 2L inequalities. Which 2L? L inequalities which say G must be non-positive, and another L inequalities which say mu should be non-negative. So, if you try to determine or identify a KKT point using just the KKT conditions, then you typically try to first solve these equations, these many equations in these many unknowns, and after getting hold of a solution or a bunch of solutions, you check each solution set against those inequalities. Okay, and if it satisfies everything, then it is a KKT point. Let us see an example. Say we try to minimize this function subject to these three inequality constraints. Okay. This is particularly relevant with inequality constraints, with which the first question is whether it is active or not. Okay. So if you know which constraints are active, then actually you have which constraints are active at the solution point which you are targeting. Then you are actually half done. Okay. So primarily, we try to identify which constraints are active at the minimum point or at the KKT point. Now, once we can do that, the actual task breaks down to known problems. Known problems, which known problems? Either unconstrained optimization or correspondingly solution of equations, something of this sort. So we don't know which constraints are active at the minimum point, so we make trials. In this particular example, in the beginning, suppose we assume that all constraints are inactive. And that means all the three Lagrange multipliers are 0. Then the rest reduces to this grad f equal to 0. Because in the gradient condition, if you put mu1, mu2, mu3 equal to 0, and there is no equality constraint either, then only grad f will survive. And this should be so because if all the constraints, all the inequality constraints are inactive, then that means it is the solution is in the interior of the domain, and that would mean that it is practically equivalent to unconstrained optimization locally. Okay, so this is an unconstrained optimization condition. So this is just a set of two equations in two unknowns, and we can solve it. Okay. As we solve, we get this point 15.5, which is the unconstrained minimum of the function. Function value is this. Then to check whether the constraints are really inactive, we evaluate the constraint functions, and find one is negative, but the other two are positive. That means it is not even feasible. Okay. So this assumption was not right. So which ones are positive? G1 and G3. So in the next trial, we revise this active set and say, suppose we say that G1 and G3 are active. So in trial 2, we say G1 and G3 are active. G2 is still inactive because we are supported by this. And if G2 is inactive, then mu2 is 0. Then we put everything in the KKT conditions again, and then we get 4 scalar conditions, scalar equations. This is the gradient equation, gradient condition. See, mu2 grad G2 is missing because mu2 is 0. And these are the two active constraints. So the constraint functions should be 0. 2 scalar equations here and 2 here. Now these two have no mu. These two have only x1, x2. So these two simultaneously we can solve for x1, x2. And then when we put them here, That is, we put grad f at that point and grad g1, grad g3 at that point. Then we get two linear equations in mu1, mu3, which we can solve. So that's what we do. We solve the last two equations to get x star and evaluate the function there, and also use the gradient condition to get mu1 and mu3. Now mu1 has turned out to be positive, as it should, but mu3 turned out to be negative. And that means G3 had no business to be active at this point. Now, since we said it is active, X star has been brought here. Okay. But if you release it, then as it goes in the interior regarding G3, then perhaps the function value will improve. So G3 should not be active. Then in the trial 3, you say that release G3 from the active set. Only G1 is active. And G2, G3 both are inactive. Therefore, mu2, mu3 are 0. Then KKT conditions will give you this as the gradient condition. G2, G3 are absent because mu2, mu3 are 0. Only this much. And G1 is active, so this is 0. So again, three equations in three unknowns, x1, x2 and mu1. Now you can solve these two together. These are two equations, two scalar equations. Now from here, you cannot solve anything completely, but you can get x1, x2 in terms of mu1. Get that? And those x1, x2 values in terms of mu1, those expressions of mu1, you insert in this, which will now give you a single equation in mu1, which you solve. So first you get mu1, then by putting that mu1 in the solution that you got from here, you get x star. You evaluate the function, and to check that the active set was really what we assumed, you evaluate G2 and G3 and find that both are negative, as they should. Okay. If you check G1, then obviously it will turn out to be 0. I mean, because that is how we got it. Okay. Now, in this trial, we find that all the KKT conditions are satisfied. And therefore, we term this point as a KKT point. And that means it has passed through the, this point has passed through the shortlisting criterion. Now, further tests, possibly in the second order, can tell whether it is a minimum point or not. After we cover second order conditions, you should check with them this point whether it stands that test and gets confirmed as a minimum point. As it happens, this is a minimum point. Now, in other applications, we have a complete class of problems called convex optimization problems or convex programming problems, which operate almost completely around KKT conditions, because in the case of such problems, KKT conditions are not only necessary but also sufficient. In particular, two big areas, linear programming and quadratic programming, operate completely with KKT conditions and need nothing else. For other utility, in algorithms, to determine a minimum point, many algorithms operate with KKT conditions at their core operational tool. And they supplement KKT conditions with some other things, which ensures that it is not only a KKT point, but it is a minimum point. But KKT conditions play a big role in the operation of the algorithms also. How to move from one iterate to another, in that KKT conditions play a very central role in many algorithms. So the combinatorial trial and error trick that we tried in the example can succeed in small problems, but that's not a method in general, because the failure of one trial in such a trick would mean nothing about the way to go for getting a good solution. It will just exclude one possible combination among the many. Okay. So that is why that is not considered as a method, but in many small problems it may work out all right. Okay. Now, even in those algorithms which do not use KKT conditions as such directly in the algorithmic steps, even there, after the algorithm has provided you a final solution, it is important that you check the solution against KKT conditions. In fact, this is a matter of professional discipline in the field of optimization, that wherever an algorithm reaches finally, whatever an algorithm puts forward to you as the final solution at the end of it, that you should always check with KKT conditions to ensure, to satisfy yourself that it is not a case of false convergence. Okay. Convergence to a wrong answer or premature termination without convergence. It is not such a case. To check that, you should always check the final point against the KKT conditions. This is a good practice that you must follow whenever you implement an algorithm. So after you have got the solution in hand, x star, corresponding lambda, mu, etc., just go on putting all those things on the left sides of each of the conditions listed in the KKT conditions, and whatever violations you get, you give it a name. Okay. And then finally you check what is the complete violation. If the complete violation is 0 or as small as can be considered as meaningless, insignificant, then you get the confirmation that yes, indeed it is a KKT point at least, and therefore might be a minimum point also, because the algorithm did a few other things to ensure the minimality and not only KKT conditions. Okay. So in summary, we can tell these things, that first, the KKT conditions of optimization, nonlinear optimization, occupy a very central role in the theory as well as algorithms of such problems. And the conditions we get by basically checking through the detailed implications of an absence of a feasible descent direction from the point. And in small and simpler kind of problems, you can even get hold of a KKT point through trial and error. Of course, using the other things that we have studied earlier, unconstrained optimization and equation solving and such things. And in general, the utility of KKT conditions come as key points in some algorithms and as an a posteriori check for all algorithms. Now, in the next lecture, we will go for the complete optimality criteria, which will give you the second order conditions, which are also necessary conditions, and then the second order conditions, which are sufficient. The way, I mean, along with KKT conditions. So the complete optimality criteria, that is conditions in addition to KKT conditions, we will talk about in the next lecture. Right now, we stop at this point.